Today we'll be doing the integral from 0 to infinity of the arctangent squared of 1 over x dx. And to start off, we will parameterize this integral. So we'll let I of m be the integral from 0 to infinity of the arctangent squared of m over x dx. And notice that I of 0 is 0 and I of 1 is the original integral. So now differentiating both sides, we have that I prime of m is the integral from 0 to infinity, the partial derivative with respect to m of the arctangent squared of m over x dx. And taking the derivative, we have I prime of m. This is going to be the integral from 0 to infinity of twice arctangent of m over x to the first power, and the partial derivative with respect to m of the arctangent of m over x dx. So we have twice the integral from 0 to infinity, the arctangent of m over x times 1 over 1 plus m over x quantity squared, and the partial derivative with respect to m of m over x because of the chain rule dx. So we have I prime of m is twice the integral from 0 to infinity arctangent of m over x times 1 over 1 plus m squared over x squared, and this derivative will end up being 1 over x dx. And now I'll simplify some things. So we can rewrite this as twice the integral from 0 to infinity, the arctangent of m over x times 1 over x squared plus m squared divided by x squared times 1 over x dx, which can be written as twice the integral from 0 to infinity of x squared times the arctangent of m over x divided by x squared plus m squared times 1 over x dx. But then one of the x's end up canceling, and we have twice the integral from 0 to infinity of x arctangent of m over x divided by x squared plus m squared dx. So from here we could use a trigonometric substitution. So I'm going to let x equal m tangent theta, which means that x over m equals the tangent of theta, which means that theta is the arctangent of x over m. So as x approaches 0, theta 1 approaches 0, and as x approaches infinity, theta 2 approaches pi over 2. So we have those bounds. And now dx will end up being m secant squared theta d theta. X squared plus m squared will be m squared tangent squared plus m squared, which means that x squared plus m squared equals m squared times, factoring in m squared, we have 1 plus tangent squared. We know 1 plus tangent squared is the secant squared. So we have m squared secant squared theta. Okay, so now plugging everything in, we have that I prime of m is twice the integral from 0 to pi over 2 of x m tangent theta, arctangent of m, we said x is m tangent theta, and then we have x squared plus m squared. We showed that's m squared secant squared, and we showed that dx is m secant squared theta d theta. So as you can see, these secant squares will cancel. This m divides to 1. This m and this m become m squared, but it will end up canceling that m squared. So we're left with I prime of m is twice the integral from 0 to pi over 2 of the tangent of theta. Arctangent of 1 over the tangent of theta could be rewritten as the arctangent of 1 over tangent is the cotangent theta d theta. And then from here we could use standard integration by parts. So we're going to let u equal the arctangent of the cotangent of theta, which means that du equals 1 over 1 plus cotangent squared theta, and then the derivative of the cotangent by the chain rule will be negative cosecant squared theta, which that means that dv is the tangent of theta, which means that v equals the integral of the tangent, which is the natural log of the secant of theta. So we have that I prime of m is twice u times v, the arctangent of the cotangent of theta, times the natural log of the secant of theta from the bounds 0 to pi over 2, then minus the integral from 0 to pi over 2 of v du. So you have a natural log of secant theta times negative cosecant squared theta divided by 1 plus cotangent squared theta d theta. And as theta approaches 0 and theta approaches pi over 2, this limit just ends up being 0. So we have I prime of m equals twice, and as you can see, these negatives end up canceling. So we have twice the integral from 0 to pi over 2, the natural log of the secant of theta times cosecant squared theta divided by 1 plus cotangent squared theta d theta, and we'll use the following standard trig identity that 1 plus cotangent squared theta is just the cosecant squared theta. So if this is just cosecant squared theta, it would end up canceling this. So we have I prime of m is twice the integral from 0 to pi over 2 of the natural log of the secant of theta d theta, but we could rewrite this as twice the integral from 0 to pi over 2, the natural log of 1 over the cosine of theta d theta. But this just ends up simplifying into, we're going to have a negative 2 integral from 0 to pi over 2, the natural log of the cosine of theta d theta. And from here we'll use the standard identity that the integral from 0 to pi over 2 of the natural log of the cosine of theta d theta just ends up evaluating to negative pi over 2 log 2, similar to the sine integral. So we have I prime of m negative 2 times negative pi over 2 log 2. The negatives cancel, the 2's cancel, so we're left with I prime of m is pi log 2. But we're not done yet. We said that I of 0 is 0 and I of 1 is the original integral. So integrating both sides from 0 to 1, so the integral from 0 to 1 of I prime of m is the integral from 0 to 1 of pi log 2 dm, which means that our original integral is pi log 2 times m from 0 to 1, which means that I equals pi log 2. So we can say, therefore, the integral from 0 to infinity of the arctangent squared of 1 over x dx evaluates to pi log 2. And so this is the final result.